In this video, we are going to discuss the systematic way of naming chemical compounds, also called nomenclature. Before you begin, you should be comfortable being able to get the charge on an ion predicted from the periodic table and have an idea about how many valence electrons are in an atom. So, what is nomenclature exactly? It is a systematic way of naming chemical compounds, and it is developed and maintained by the IUPAC, which is the International Union of Pure and Applied Chemistry. And it's critically important that we have a systematic way of naming because it aids in communication between scientists around the world, and it would be impossible to memorize all compounds. There's nearly an infinite amount of ways that we can combine atoms to make new molecules, and by having a systematic way of naming them, everybody can know what we're talking about even if we discover something new. So we're going to start with ionic compound. The first type of ionic compound is type 1. And we're going to be looking at binary, meaning there's only two elements, not two atoms, but two elements. We're going to list the cation first, followed by the anion, and we'll change the ending of the anion name to "ide." Now, these are type 1 because the cation has a consistent charge. So that means groups 1, 2, and then a couple of special transition metals, cadmium, silver, and zinc. And so as an example, if we had the cation first, say sodium, and then we have the anion, chloride, these come together to make a formula NaCl, and we name it sodium chloride. Note that we don't say sodium ion chloride ion, we just say sodium chloride, and that the formula unit does not have a charge because the charges are balanced. If you don't remember how to do that, you might want to go back and review the compounds video. So let's do some practice. We have a strontium and we have bromide. So the nice thing about these type 1 binary compounds is that the charges tell you exactly how many of each ion will be in the formula unit. And so if I say strontium bromide, you automatically know that the formula is going to be SrBr2 because strontium only ever makes up 2 positive cation and bromide is a negative. And so we don't have to do anything when we name strontium bromide. We can just say the names of the two ions. And the same goes for the next two. So here we have magnesium and then an oxygen atom. And the way that you turn oxygen into an ion is to call it oxide. So we simply write magnesium oxide. And then finally, we have a potassium. And then phosphate becomes phosphide. Now remember, you change the ending of the anion to "ide" when writing these formulas. So let's practice writing the formula. When I do this, I like to start by writing the ions so that I can see the charges. So calcium has a 2 plus ion, and oxygen, oxide, is 2 negative. And so that means that we have a 1-to-1 ratio here. And so I simply write CaO. Remember that we want to have the least common denominator, so we want to use the smallest ratio possible. And so we could say 2 to 2, but that isn't the actual repeating formula unit because it's really just a 1-to-1 ratio. And so we just write it as CaO. And now for potassium chloride, we have a K positive and a Cl negative. And these both have a 1, positive 1, and a negative 1. So then we just simply write potassium chloride. One thing that's really important when you're writing these is to be consistent with your letters. So your first letter is always capitalized and the second one is always lowercase if you have a single element, and each new element starts with a capital letter. It is critically important that you write it this way because if you were to use, say, an L here, that would look like a capital L, that would look like a potassium, a carbon, and then some unknown element that's just L. And so you want to make sure that you're very clear when you write these. Okay, lastly, magnesium nitride. So we've got a magnesium, which has a 2 positive, and a nitrogen, which has a 3 negative. So here you might want to use that little crisscross trick where you take the charge on the cation and make it the subscript on the anion, and vice versa. So we say magnesium, and then the subscript becomes 3, and then nitride, and the subscript becomes 2. So now we're going to move on to the type 2 ionic compounds. So these follow the same rules as type 1. We still name the cation first, followed by the anion, and we end things in "ide." But the difference is the cation has a variable charge. Now, the anions always have a consistent charge, and so we are going to use the charge on the anion to interpret the formula if we see the formula unit, and we're going to use a Roman numeral when writing out the name. This simple periodic table shows some of the compounds that have variable charges. One of the more common ones that you will encounter: iron, copper, possibly cobalt or chromium, and then lead and tin as well. So first, cobalt and nitrogen. So nitrogen makes a -3 charge. And then that means cobalt has to have a +1 charge here because there are 3 of them and they have to balance. So we would write cobalt, and then we put the Roman numeral 1, and then nitride. This tells everyone that the cobalt is a +1 charge. If you simply wrote cobalt nitride, then we wouldn't know what the charge on the cobalt ion is. Now we move to lead iodide. We know that iodide is a -1 charge, and there are 2 of them. So that means that lead must be 2+. So we would write this as lead 2 iodide. This compound was one that was called, I think it was called iodine yellow, and this was one of the paint pigments that used lead back in the day, and it is no longer used because it is obviously incredibly toxic. Okay, this compound, iron and oxygen, we know that oxygen is a 2 negative, and there are 3 of them. So we have a total of -6. And so that means that our 2 irons are going to be negative or +3 each. So it will be Fe3. 3 plus. And you'll notice how we can look, it's kind of like the reverse of the crisscross trick. We take the 3, that is the subscript on the oxygen, and make it the superscript on the iron. And then we take the 2, that is the subscript on the iron, and make it the charge or superscript on the oxygen. And so we would write this as iron 3 oxide. And this is one of the common things that happens when iron rusts. So now the name to formula is pretty easy. We know that oxygen makes a 2 negative, and it's tin 4. And so you just make this a number. So it'd be tin and it's 4, and since it's a cation, it's always plus. And so now we have tin oxide. Iron 3, and then bromide is a negative 1, so we end up with FeBr3. And finally, copper 1 sulfide. Sulfide is a 2 negative, and copper plus 1 because it's a 1. And so it is copper, and there are 2 of them, and a sulfur. Now we are ready to move on to naming covalent compounds. When we name simple molecules with covalent bonds, we have to indicate the number of each atom when writing the names, and we use subscripts to indicate the number of each atom when writing formulas. So for example, if you want to write out the name, the scientific name for water. So we know that water has 2 hydrogen atoms and 1 oxygen atom. And so that means that in our formula, we have to indicate that there's 2 hydrogens for every 1 oxygen, and so we write it like that. Now, if we were to write out the systematic name, we would have to use these prefixes because we can't just say hydrogen oxide because there are many compounds that contain only hydrogen and oxygen. And it's not charged, so we can't tell necessarily how many of each atom is involved. And so if we were to just write out hydrogen oxide, that wouldn't work. So this is where we get these prefixes. So since there are 2 hydrogens, we would say dihydrogen. And then there's 1 oxygen, and so we use the prefix mono. And when it is a vowel, especially when it's an O, we drop one of the O's here. So instead of writing monoxide, we just write monoxide. And you'll see this fairly frequently. Another example would be with carbon. We can't just simply say carbon oxide because we've got CO, we've got CO2, and so we can't say just carbon oxide, and there's no charges to tell us how many of each atom are there, so we would just write carbon monoxide or carbon dioxide. Note that because carbon is a single one and it is the first element, we don't say monocarbon monoxide. We just say carbon monoxide, carbon dioxide. So let's do some practice. Here we have a phosphorus and we have bromine, and there are 3 of them. So phosphorus, and again, we don't say mono because it's the first one, and then tribromide. Here we have a silicon, and then dioxide. Here we have xenon, And then there are 6 fluorines attached to this. And so that is hexafluoride. And then here we have a 2 on our nitrogen. And so we can't leave the di out of that. So it's going to be dinitrogen pentoxide. And again, penta ends with a vowel, and then oxide begins with a vowel. So we don't write pentaoxide, we just write pentoxide. Practicing name to formula. Carbon monoxide, so a single carbon and a single oxygen. Boron trihydride, so that means a single boron, and then there are 3 hydrogens. Dinitrogen pentoxide, N2O5, and tetraphosphorus heptasulfide. So there are, tetra means 4, phosphorus is a P, hepta means 7, sulfur is an S, so we would write P4S7. Lastly, we want to talk briefly about polyatomic ions. These are atoms covalently bound, and they form this molecule, and then the molecule as a group loses or gains electrons. So we have to use parentheses when a subscript is needed because we have to apply the subscript to the whole ion. So you've seen this before in math. So for example, if you have 2x squared or you have 2x squared, these mean 2 different things. So this is actually 4x squared because you apply the square to both the 2 and the x. If you actually mean this and you write this, you'll get the wrong answer. And the same idea goes for these polyatomic ions. So for example, hydroxide is one of the polyatomic ions, and it is a oxygen and a hydrogen, and the whole thing has a negative charge. So that means that when you're using hydroxide in a formula, if you have to have more than one of them, you want to use parentheses. So 2 hydroxides means you have 2 of these. And if you had simply written OH2, that just looks like you wrote water weird. So we want to make sure that we're keeping track of our polyatomic ions. Now, you don't need to memorize them all. However, you do definitely need to work with them often enough that you become familiar with them and can recognize them when you see them. So this chart is available in your textbook, and I like it because it's pretty and it can help if you like the colors. There are other charts as well, but these are some really common ones. And this actually shows how the atoms are connected to each other, which is why I really like this picture here. We'll be working on constructing these shapes later in the week. So here we have hydroxide, and you can see it has a O and an H. They are covalently bound to each other, and then it has a negative charge. And so up here we have a carbon, and it's bound covalently to these oxygen atoms, and it has a -2 charge. So all of these polyatomic ions have 1 charge. So just like when we did the binary ionic compounds and we looked at charges and how they're consistent for the anions and the type 1 cations, these polyatomic ions all have a consistent charge every single time. So you don't have to question that. The carbonates here, -2. Acetate is -1. Hydroxide, -1. Sulfate, -2. Phosphate, -3. and so on. And we will do some practice now with naming compounds and writing out the formulas for compounds with polyatomic ions. So here is the table that you will have for the exam. So you don't need to memorize all of these, but you may want to refer to it when you are working on these problems so that you can practice answering, you can practice naming these compounds with the table that you will have access to on the exam. So here we have formula to name. So the first thing you want to do is identify where the ions are. So here we have ammonium, and here we have chloride. And so ammonium is actually the polyatomic ion, and it's +1, and chloride is -1. So we simply just have to write ammonium chloride. Now, you don't need to worry about Roman numerals and you don't need to worry about prefixes because the charges are consistent, which means that you always know from looking at the formula or looking at the name exactly what the compound is. Here we have aluminum, and here we have sulfate. So you can see how this indicates that you need 3 sulfates to balance the charges of 2 aluminums. And that makes sense because aluminum is a 3+ charge and sulfate, the whole thing, has a -2 charge. So we simply write aluminum sulfate. We have sodium, which you should be able to recognize, and that's our +1. So that means that this here must be our polyatomic ion. And it has a charge of -1. Now, this one, it has 2 names, and you can use either one. One way to name this is sodium hydrogen carbonate. And that's because carbonate is the main polyatomic ion and it can take on some hydrogens. So it is a hydrogen attached to a carbonate. Or this would also be called sodium bicarbonate, which you may recognize as baking soda. And finally, we have a potassium and a phosphate. So we simply write potassium phosphate. And we know that we need 3 potassiums from this name here because potassium is a +1 charge and phosphate is a -3 charge. So now we're going to practice going from the name to the formula. So we want to start by writing out our ions so that we can see what the charges are. So here we have sodium, and then acetate. Acetate's kind of long, and there are a couple different ways to write out the name. One way is CH3CO2, and it has a negative charge. Or some people like to write it as C2H3O2 with a negative charge. I like this one. So I would write this as sodium acetate or sodium and then CH3CO2. Either way is acceptable. Calcium nitrate. So nitrate, NO3 with a -1 charge, and then calcium has a 2 positive charge. So we would have to use our parentheses here to indicate that we need 2 of these. So calcium nitrate. Now we have potassium carbonate. It's going to be similar to what we did before. Here we have our 1 charge, and carbonate has a 2 charge. And so we don't need parentheses for the potassium because there's only one of those. So we can just write it as K2CO3. Lastly, iron sulfite, and this is iron 2. So we can start off with iron 2, and then sulfite is SO3, and it has a 2 negative charge. So we would write it as FeSO3. It's a lot of information, but I've broken things up into chapters, so you should be able to review just the sections that you're struggling with or practicing at the time. The only way to get good at this is to practice. There's no real magic. It's just practice. And I have found that flashcards can be effective for remembering the polyatomic ions, but I have found that most students are more successful when they actually practice writing these things out. Good luck!